Okay, so you already saw this slide yesterday. By the way, I made a small mistake because the case AN correspond to the group ZN plus 1, actually. And in the other groups, the N are the dihedral groups, E6, E7, E8 are the tetrahedral, octahedral, and icosahedral groups. Part of the McKay correspondence is the fact that this group corresponds to some Dinkin diagrams, which in turn are the Dinkin diagrams associated with root systems of the simple Lie groups. And let me explain this a little bit, although it's not really, how to say, main part of what I want to tell you, but I would like to mention that because it looks kind of mysterious. And then I will concentrate more on the geometry of the thing. So it's simply the following. If you fix a finite group, inside, well, actually at the end of the day is inside SU2, talking about 2 dimensions. And so it has the defining representation that I will call V. So as a vector space, it is isomorphic to C2. And I will call rho I the irreducible representation. And then, due to reductivity, if you want, if you take a tensor product, V times one of the irreducible representation, this is written on the irreducible representation themselves with some multiplicities, right, given by the matrix A. Okay, and then to this you associate a quiver. A quiver in the following way: vertices are the irreducible representations, and there are Aij arrows, so edges, actually they are not oriented, between the vertices I and J. Okay, so this allows one to draw a graph, a quiver. The quiver turns out to be a Dinkin diagram of the root system of some Lie group, and Ij is the Cartan matrix of the associated Lie algebra. Okay, this is group theory. Now what happens is what's written in the lower left corner of this slide, namely the fact that here in this sentences, I talk about the exceptional divisor of the resolution of singularities. Now, what happens, the exceptional divisor is what you replace. You replace the singularities with, as I was saying also this morning during the discussion session, when you desingularize, you replace the singular locus with some close, something which becomes a close subset of the resolution of singularity, which is called the exceptional locus. And in this case, the exceptional locus is a subvariety of codimension 1, so a line, a curve, sorry, which in general is reducible. It has several components. So this is the exceptional divisor I'm writing here. I'm mentioning here, and so it has several components. And the miracle is that these components have an intersection pattern which is exactly given by the linking diagram associated with the group you are considering. So I can make a very ugly drawing. The idea, for instance, if you consider something like this, and I wrote this already in another slide, but the idea is that the action of Zn is given by this generator. Okay, and you consider the resolution singularities, exactly what for Z equal to 2 I was doing explicitly using toric geometry. But we also had the slide where this was done in a case of a bigger n, right? For instance, this is the case of A3, which is the case of the action of Z4, where again, using toric geometry, you start from a cone, and now to get a collection of smooth cones, you have to divide the cone into 4. According to this pattern, and in this way you get resolution singularities, which is a smooth, in this case, toric variety. And the pattern I was mentioning is the following. So in this case, it's something like this, right? In this case, the only singular point in the quotient is the one corresponding to the origin. So you have the origin here, which is a singular point, and what you do is to replace it with the resolution singularities. You have something that, if you remember, I could also make a different drawing, because I could say that up here I replace so the exceptional divisor. These are the components of the exceptional divisor. It could be something like this. So here I look at them as projective lines, but I can also remember that projective line topologically is an S2. So what happens is what is depicted on the left, right, where I replace the origin with an open necklace of spheres, right? Each sphere is one irreducible component of the exceptional divisor, and the idea is that you see in this case you can compare this with this linking diagram. Okay, and this is for sorry, one more. These were 5. Okay. So this is situation for the action of Z6. And it is therefore the linking diagram of A5. Okay? Well, this is a geometric part of the McKay correspondence in 2 dimensions. Now we can write formulas, or we can write mathematical sentences instead of drawing. And then what happens is that in the resolution singularities, so you see, we are talking about a complex surface, so real dimension 4. These spaces have no odd dimensional cohomology, because the cohomology is exactly generated by the components of the exceptional divisor that are real even dimensional. What happens is that H0 is 1-dimensional, just because the spaces are connected. H4 is 0, because they are non-compact, orientable non-compact, and therefore all relevant cohomologies in degree 2. And what happens is that every component of the exceptional divisor is a generator of this second cohomology group. As you see, these irreducible components have some intersection pattern. This intersection pattern can be computed in cohomology because you can intersect cohomology classes. Actually, this is well defined because these cohomology classes have compact generators. So, okay, the cohomology is compactly supported, so computing the intersection makes sense. We have, in other terms, a well-defined intersection form on the second cohomology group, and this happens to be exactly minus the Cartan matrix of the root system of the corresponding Lie algebra, right? In our correspondence, we also have a Lie algebra. This has a Cartan matrix, which group theoretically is this matrix Ij, and geometrically, this matrix is up to a sign given by the intersection pattern of the components of the exceptional divisor. So you have, if you take the two different components, you have either 0 or 1, according to whether they intersect or not. And the diagonal -2 relates to the fact that there is a well-defined self-intersection for these cohomology classes. Of course, you have a well-defined intersection form, so you can take the square of the generator, and the result is -2, related to the fact that these are, from the point of view of complex geometry, they are compact curves or projective curves of genus 0. So this is, in a nutshell, McKay correspondence in 2 dimensions. Okay, so perhaps I stop here and ask if there are any questions.
There's no questions so far.
Okay, so now I go to 3 dimensions. I'll be back to 2 dimensions again as a starting example when we consider how to construct in general the resolutions of singularities. In 3 dimensions, the situation is clearly more complex, more complicated, and an important notion is that of age. To be precise, of conjugacy classes of elements of the group. In the abelian case, of course, an element is the same thing as its conjugacy class. In the non-abelian case, this is not true. So the right association is the fact that the age is a property of a conjugacy class. So if we have an element in the group, since the group has a finite order, it's finite, there's an integer r such that gr is equal to 1. And then what we do is that we consider the eigenvalues of G, right, as a matrix in SL3C, and we write them as a power of a primitive root, rth root of unity. Okay, and so we get 3 numbers, AI, and we compute the normalized sum. So we sum these numbers, AI, so basically related to eigenvalues of the matrix representing the group element, and we divide by R. It turns out that due to the fact that this group acts inside the set 3C, the age can have 3 values, 0, 1, and 2. Actually, only the identity as age 0. And then we call the classes whose age is 1, we call junior. in the classes whose age is 2, we call senior. Okay, so we have either up to the identity. So we have either junior or senior classes. And we write gamma I for the set of conjugacy classes of age I. Let me make an example which will be a kind of guiding example, simple enough to understand everything, but already with enough structure to serve as a good example. So we consider Z4 with an action on C3 given in this way. Okay, this G0 is the generator of the action. I is the imaginary unit. This is clearly an action of Z4, the representation of Z4. And of course, we have four elements, the identity G0, G0 square, and G0 cube. And we see that G0 and G0 square are junior, and the G0 cube is senior. It's a very simple computation, right? You compute simply. Everything is diagonal here, so you get immediately the answer. So you see, for instance, G0 square, the three numbers are 2, 2, 0. In this case, R is clearly 4, and therefore the age is 1. Okay? G0 cube, the three numbers are 3, 3, 2, and you get that the age is 2. So this is the only senior class. And this is the big theorem, of which whose proof is kind of complicated. So we shall try to understand it by way of example. And this is the analog of the simple constatation that we made of the fact that in 2 dimensions, the irreducible component of the exceptional divisor generates the second cohomology group. In this case, the non-trivial cohomologies are in degree 2 and 4. Okay. Again, H6 is 0 because this variety is compact and non-compact oriented. And so we should take care of H2 and H4. And also we shall make a distinction between, we shall consider, let's say, not only the say usual cohomology groups with coefficients in Q, but also cohomology groups with the compact supports. Why this? Among other things, the reason is that in this case, you have a Poincaré duality, because if one of the two factors is compactly supported, there's a well-defined notion of pairing. So you can do things like this. And this is a non-degenerate pairing. And so if you want, you represent cohomology classes with differential forms, and you replace, so they are compactly supported, if you consider them in a compact supporting cohomology group, and then you integrate on the homology duals of the cohomology classes on the left, right, or vice versa. So you get a well-defined Poincaré duality, right? So you can switch from cohomology to compactly supported cohomology and vice versa. And the theorem says the following, that there is a one-to-one correspondence between, for instance, the set of senior conjugacy classes, the compact exceptional prime divisor of the resolution singularities. Here, just to confuse ideas, I changed the notation. And the reason, of course, is that I'm taking slides from different sources. I'm sorry for that. X is the singular quotient, and Y here is the resolution singularities. Okay. So, and here also the notation is slightly different. The terminology, this is taken from algebraic geometry. I talk about compact exceptional prime divisors. So prime means that I'm considering the irreducible components. Okay. So we are saying that each senior class corresponds to a compact irreducible component of the exceptional locus. And in this way, we get a basis of the second cohomology group with compact supports. If you want, since we have Poincare duality, this is also a basis of H4, right, by duality. So senior conjugacy classes are, they correspond to compact irreducible components of the exceptional divisor. And in this way, they provide the basis for the second cohomology with compact supports. What about the junior classes? Actually, they are in correspondence with all components, compact or not. We shall see that, for instance, in the guiding example of C3 mod Z4, there will be one compact and one non-compact component. So since we have all irreducible components of the exceptional divisor, we get a basis for the full second cohomology group, which again, by Poincare duality, is a dual basis for the fourth cohomology group with the compact supports. You see, in our guiding example, we have two junior classes. So that means that altogether we have two components for the exceptional divisor. And we have just one senior class. So that means that we have one compact component. So altogether, we have one compact and one non-compact component. As a trick of the trade, I mean, now it happens that the junior components correspond one to a compact and one to a non-compact component. The trick of the trade to understand which is that one of the junior classes has a 0 in the triple of numbers we are considering. This is the non-compact, because that means that this arises when you resolve the singularity due to a full line, non-compact singular locus. The other one, 112, no 0, this is compact, and it's the component of the exceptional divisor which resolve the singularity at the origin, okay? Which is clearly a compact subset of the singular quotient. Okay, again, we have this quite striking, to my viewpoint, correspondence between the simply the structure of the group and the geometry of the resolution of singularities. Which, by the way, in general in 3 dimensions is not unique. So, but if Y is a resolution of singularities, you have this situation. In the case of the guiding example, there's the resolution of singularity, which, as I was mentioning, in 3 dimensions always exists. The crepant resolution of singularity, which always exists, is unique. So this is a resume of what happens in our guiding example. Okay, so we are resolving, we are considering a crepant resolution of singularities of the singular quotient C3 mod Z4. From the theorem, you forgot to say that to Ito and read, we realize that the fourth cohomology is one-dimensional, the second cohomology is two-dimensional, and therefore H2 compact is dual to H4, and therefore it's one-dimensional as well. So again, the exceptional divisor has one compact and one non-compact component. Now, since Z4 is abelian, we can study the geometry of this problem using, again, toric geometry. And now again, in some way, I should get out of the hat a cone which describes C3 mod Z4. Okay, what happens is that C3 is quite clearly a toric variety. It's a toric variety, affine, of course, which corresponds to the cone, which is the first quadrant of R3, or the first octant, sorry, of R3, right? Generated by the three standard basis vector for R3. The fact that it is toric means that there is an action of the standard torus, namely, what I'm saying is that we have the standard three-dimensional torus, which is the product of three copies, with torus in the sense of algebraic geometry. So it's a product of three copies. This, of course, acts on C3, and the action commutes. It's just a diagonal action. In a trivial way, the action commutes with the action of Z4, which is diagonal as well. As a result, the quotient is a toric variety. So in this particular case, we understand this very well. And therefore, as an affine, of course, is affine. And as such is described by a cone. So it can be written as the affine toric variety associated to a cone in R3. Then, of course, one has to know how to compute a cone. This is the standard elementary thing. I cannot explain everything, unfortunately, but it's an easy procedure in toric geometry. And for instance, of course, there is no uniqueness in this. One can take the cone, which is generated by these three vectors. 0, -1, 2, -1, 2, 0, and 1, 0, 0. Now, if we organize these vectors in a matrix, we get the following. Right, and the determinant of this matrix is 4. And indeed, we are describing a singular variety. Of course, 4 is no accident, the fact that we get 4. Again, what to do? We can obtain a resolution of singularity splitting this cone into a number of smooth cones. Okay, cones, each of which, all of them generated by a triple of rational vectors, which are a basis of Z3. There's a way of doing that. Since we are looking for a Krepan resolution, something which is, variety which is going to have a trivial canonical bundle, the recipe is the following. So one can try this and see if it works. You see in the drawing in the lower right corner is the lattice. Okay, so the blue points are the point in the lattice that we may think have Z3. Okay. And the black arrows are the generators of the cone. You take the triangle whose vertices are the tips of the three vectors, and you look for the points of the lattice that lies on the triangle. And it's an easy combinatorial theorem that what you get, so you get two, in this case, you get 2 points. So you get the 2 new vectors that in this drawing here are in red. Okay, they are in red. And it's a simple, in this way, the cone is split into 4 cones. And it's a simple combinatorial theorem that every cone that you get in this subdivision is smooth. Is formed by, is generated by a basis of Z3. So the drawings in the lower left part of the slide are something, these diagrams have different names, either planar graph or the junior simplex or whatever. So the triangle with vertices V1, V2, V3 is basically the gray triangle on the right. And then you see that we found 3 integral points in this triangle, which I call W3 and W2. In toric geometry, the rays in a cone or in a fan correspond to divisors, namely to irreducible subvariety of codimension 1. And therefore, W2 and W3 correspond to 2 divisors. And these are the 2, of course, these are 2 divisors that we are adding, right? Because we are adding these 2 new rays, W2, W3. So we are adding 2 divisors, and these are the irreducible components of the exceptional divisor. And actually, you see, toric geometry is kind of magic because you understand a lot of things simply by doing elementary manipulations. We have split the planar graph we started with just by adding W2 and W3. So the unique cone, which is the yellow triangle on the left, has been split into 4 cones. The cones of 4 different colors in this triangle, in this graph. W3 is in the interior. W2 is on the border. The result is that the divisor corresponding to W3 is compact. The divisor corresponding to W2 is non-compact. And if you now use toric geometry to compute them, you realize that the compact component is a copy of the second Hilbert surface. And the non-compact copy is P1 times C. What has happened is the following. In our original, so now here downstairs we have C3 mod Z4. So we have the origin, which is is a fixed point of C3. Therefore, it generates a singular point. But if you look at the action, which let me recall, since the 3 coordinates x, y, z to ix, iy minus z, points on the z-axis are invariant under a Z2 subgroup. Which is exactly the subgroup generated by our G0 square. You see here G0 square, right? If a point has coordinates 0, 0, z, it is invariant, right? So G0 square generates a Z2 subgroup of Z4, which is the isotropy subgroup of every point on the Z-axis. As a result, the Z-axis in the quotient is singular as well. So we have a line of singularities. Yeah. Okay, and which is the Z-axis. And therefore, what happens is that when you resolve this, of course, you get something inside the resolution singularity which sits above, sorry, this singularity. So it is, and indeed, it turns out that this is a space which is P1 times C, or C times P1, where C is the Z-axis, actually. You may think of it as the axis, and then you have fibers that are copies of P1. Altogether is compact. And then you have sitting only above the origin something which is compact and is a copy of the second Hilbert surface. What is the second Hilbert surface? There's some different ways of telling what it is. What you can do, for instance, is the following. You take the direct sum of the trivial line bundle on P1 with the bundle O minus 2 on P1, and you projectivize this. The total space of this is a threefold, and you projectivize this. So basically you projectivize the fibers, right? This is a vector bundle of rank 2 over P1. So every fiber is a two-dimensional vector space, and you projectivize it. And this is F2, where 2 is because we took O minus 2. F2 is actually turns out to be, as all Hilbert surfaces are, exactly by the same construction, a P1 fibration over P1. Okay? The P1 fibrations over P1 are classified by a natural number. When the natural number is 0, you get the product, P1 times P1. And when the number is positive, you get a new trivial fibration, which is called the nth, if the number is n, it's a book surface. Okay. So in particular, projective and in particular, compact complex surface. So this is what we get in our case, in our guiding case of C3 modulo Z4. Any questions up to here?
Don't see any questions.
No questions. Let me see what we can do. Okay, so what we saw today so far was the McKay correspondence in two dimensions. Actually, we saw two aspects of the McKay correspondence, right? An aspect which relates our finite subgroups of SL2C to quivers and to linking diagrams of simple Lie algebras. And on the other side, we saw correspondence between these structures and the structure of the exceptional divisor of the resolution singularities. In three dimensions, I only mentioned the second part, basically, right? I didn't mention anything replacing the linking diagrams. However, this can be done in the sense that one can up to a point, one can associate to these groups acting in three dimensions quivers. And by the way, a very powerful theorem tells that also in three dimensions, the same thing that happens in two dimensions is true, something that I didn't mention, but the fact that the resolution singularities are actually modular spaces of representations of these quivers. Okay, so another approach to these spaces could be just to go through the quivers and study, study the modular space of, the modular space of representation of the so-called quiver algebra, something which, has been done and researched quite a lot in the last, I don't know, 20 years. The point is that in three dimensions, this is really quite complicated. The approach via quivers is really very complicated, but anyway, it's doable. What I would like to do now is to say a few words about the construction of the resolution singularities in a more general way, and also more related actually to the K correspondence. So not using this toric magic, which only works in the billion case, but more in general. And let me start again in two dimensions, where the resolution singularities of the quotient C2 mod G, and again we should stress that G is a finite subgroup of SL2C, okay, SL2C. These are called ALE spaces, where this acronym means asymptotically locally Euclidean. The reason of this terminology is that these spaces come with the hyperkähler metric, which has an asymptotic structure at infinity. It approaches the Euclidean metric in a well-defined, with a well-defined behavior, asymptotic behavior. Actually, there are two approaches. Either using, just use being a little brutal. One can either use differential geometry, and then one performs what is called a hyperkähler quotient, or in algebraic geometry using so-called geometric invariant theory. This is a small pun in the sense that if you Google ALE, of course, in particular, you can even Google ALE space, and if you Google ALE space, this is what you get. You see, it's even written on the glass, third space. It's a nail whose name is third space. Okay, so in principle, we have two approaches, two routes to follow to construct the resolution singularity. They produce the same result in a sense that I will specify in a moment. So what you do is the following. You take the regular representation of our group. The regular representation is so what you do is the following. You take the so-called group algebra. It's written here at the bottom of the slide in the footnote. You take the group algebra, namely, you take the vector space generated by the elements of the group. Okay, so an element here is a formal sum of elements of the group with some complex coefficients. And this, of course, carries an action of the group just by multiplying. Now, if you have an element which is a sum AI, GI, and you have an element H, you simply consider this, and this gives an action of the group over its group algebra. This is called the regular representation. So you take the endomorphisms of the regular representation times C2. This carries in a natural way an action of the group G. Because G acts on C2, it acts on the regular representation. And you take the invariants. So PG is the invariant subspace. I call it M. On this space, there's an action of this group. This is the G invariant part of the, I mean, not the G invariant part, this is the subgroup of the unitary group of R, which commutes with the action of G, so which is compatible with the action of G. And also, since there's an invariance under homotheties, we also take the projectivization of it. So we have a Lie group, this Lie group, and we take its Lie algebra. And then we define a moment map, which is actually a triple of moment maps, right? So it is a map from the manifold to R3 times G star. And these are the three explicit, here the moment map is written explicitly. And what happens is that if you take the zero level space of the moment map and you take a quotient by the group script G, what you get is the singular quotient. And then the idea is that you desingularize the quotient by perturbing the zero level set of the moment map. In particular, what you can prove is that if you take a generic element in the center of the dual of the Lie algebra, then the group G, usually called the gauge group, acts freely on the level set. And then if you take the quotient, you get something which is smooth. And indeed, you can prove that you get a resolution of singularities of C2 mod G. Clearly, we get the resolution of singularities in the category of complex manifolds, right? Because here everything is complex analytic, not algebraic, I mean. It turns out that X theta is a hyperkähler manifold. Okay, one should also say that as a manifold, it doesn't depend on theta. Okay, in the sense that you must avoid zero, but for instance, if you move theta a little bit around zero, the manifold that you get is always the same. This is true for every generic value of theta. You get the same manifold. This manifold comes with some geometric structures, additional geometric structures, which I will mention at some point. And these structures depend on theta, but not the manifold itself. And this manifold happens to be a hyperkähler manifold. The Reason being in particular that we started from actually not really a moment map, so we are not simply getting a symplectic manifold, but we are getting a hyperkernel. Of course, I'm simplifying the story very much because you get a hyperkernel manifold because from the beginning you equip the space P with a hyperkernel structure. Then this will be compatible with the action of the gauge group and will descend to the quotient. One can do this also in algebraic geometry. And then the procedure here is the following. One can rearrange these three components. You see that these three components all involve taking an Hermitian conjugate. But as a matter of fact, you can rearrange these in such a way that only one of them will include Hermitian conjugates. And therefore, you have a part of this moment map which is holomorphic. It doesn't involve any compact conjugation. You do that, and then you realize that actually it's not only holomorphic, is even algebraic, right? So from the original vector space P or M, right, which is an affine variety, we cut something using polynomial equations, so we have an affine variety. So we are now in algebraic geometry. And then, of course, now still you have the problem that if you take just the quotient now, you get something which is singular. And there's a way in algebraic geometry to select a subset of the space in such a way that the quotient is going to be smooth. This depends again on the choice of a parameter theta. And what you have to do is to look for the points that are stable in a suitable sense. I'm not going into explaining what the geometric invariant theory is. I only want to say that there's also a way of doing this as an algebraic variety. And then we get a quotient, which you see I used a different font. I called it script x theta. We get a quotient which is a smooth algebraic variety. And this is a resolution singularity of C2 mod G. The two constructions are compatible because at the end of the day, as I was mentioning perhaps yesterday, answering to a question, when we have an algebraic variety over C, we can think of it also as a not a complex variety because it may be singular in general, but as what is called an analytic space. Namely, in particular, we may keep it not with the Zariski topology, but with the Euclidean or analytic or classic topology. In our case, this variety is even smooth, and therefore it has an underlying structure of a complex manifold. It has a complex, I mean, it admits a complex structure in this as a structure of complex manifold. As such, right, this X script N, so the same space regarded as an analytic variety, is isomorphic to the resolution that we made using Cronheimer's hyperkähler reduction technique. Okay, so the two constructions are compatible in this way. And the same thing happens in 3 dimensions. So you have a generalization of the Cronheimer procedure, which was studied in a PhD thesis in Oxford by a guy called Sardo Infirri. So you have exactly, and we like to call it a generalized Kronheimer procedure because it's exactly the same. Or as using geometric invariant theory. Using geometric invariant theory, you can look at these desingularizations as a modular space of a very interesting sort of geometric objects, which are called G constellations. And since and this has something to do with the question I was asked this morning about the K-theory of the resolution singularities. So perhaps tomorrow, I guess, I will speak a little bit about it. Or not, or now. Now, I will start now. I will stop to ask if there are any questions. Please ask a question.
Sorry, can I ask a question? That modular space that you obtain, that have some structure like hyperkähler Keller structures.
No, in this case, it's scalar. I mean, the analytic version of it, it's scalar. Cannot be hyperkähler because it has the wrong dimension, right? Because the real dimension of a hyperkähler manifold is a multiple of 4. So, and this happens indeed for quotients of C2. They happen, and the resolutions, they happen to be hyperkähler. Cannot happen for C3, the quotients of C3, but they are Kähler. And again, what you do is you see, just forget that these formulas have been written in 2 dimensions. You do something quite similar. The original, the flat quotation mark space that you start with is scalar in a trivial way. It's a flat Kähler space. It's a, I mean, a Euclidean space with the Kähler structure. And this is preserved by the gauge group, so it goes down to the quotient. And yeah, the quotient is scalar. It has much more structure. And indeed, what I would like, I mean, I think it's 2 minutes to 3. So really, it's time to go on with the questions rather than introducing new stuff. I will talk about that tomorrow. So I will stop here.